Hi everyone. Thanks for coming. It's today my great pleasure to welcome Robert Taylor at CQT. Robert is a professor of experimental physics at the Clarendon Laboratory in Oxford, and he's also the deputy head of the university's division for mathematical, physical and life sciences. So when he's not doing admin for the university, you can find him in the laboratory, where his main interests are in the optical characterization of low-dimensional structures such as quantum wires, wells, and dots in wide bandgap semiconductors. His most recent work includes single photon generation from quantum dots of the gallium nitride type, so in the blue wavelength range, but also photonic crystal microcavities, of which we'll hear more about today. And even coupling energy transitions in living bacteria to microcavities. So more on all those things from Robert. Thanks.
Okay, thanks, Tristan. So, as Tristan say, I've got three main projects I'm working on at the moment, and I thought today I'd talk about the Photonic Crystal project, which is a collaboration between the University of Oxford, Imperial College in London, and Hitachi Cambridge Laboratories. And the reason that we have a close collaboration with Hitachi is that they have in Cambridge a very good E-beam machine made by Leica, which is very well corrected for writing these photonic crystals I'll talk about during the talk. And so the actual photonic crystal writing is done in Cambridge, and we do the optical experiments in Oxford. And so Fred Brossard is the collaborator in Hitachi, and Ben Reed's my postdoc, and these are my graduate students who worked on this project. And Phil Spencer and Ray Murray have been growing the samples and also doing some measurements in magnetic fields in Imperial. But I'm not going to talk about the magnetic field measurements today, just the main optics. Okay, so I'll start by giving a very general introduction to photonic crystals and photonic molecules, why we're interested, why bother. And then I'll talk a little bit about how we can change the tuning in our crystals from coarse to fine, and this is the extra bit we've done here. And then at the very end, just before conclusions, I've slipped in some new data that we're just about to submit to the ICPS conference, which is in Beijing this summer, where we're using photolithography rather than E-beam to actually make the cavities, which is actually a new technique we're using, and it's working very well. Okay, so single photon sources using quantum dots have been around for quite a while. There's a paper in 2002 by Julian Wan, who just started working in Toshiba at the time, where they made a little single photon source here. But they all worked, and up till now, at about 980 nanometers. The reason people are interested in doing it at 980 is because silicon APDs work very well at those wavelengths, so you get very high efficiencies. And so it's been a very easy, or I say relatively easy experiment to do. The trouble is, almost all the telecom infrastructure in the world, if you actually want to send data in single photon patterns through fibers, runs at 1.5 microns. So really what you want to do is to actually shift this whole field from 980 nanometers down to 1.55 microns. Turns out that's quite hard to do for two reasons. One, detectors are very poor at 1.55 microns. But secondly, it's actually quite hard to make quantum dots that work at that long wavelength. It turns out, though, that you can actually make dots that work at 1.3 microns, which is the other telecom band, reasonably easily. So we've started working at 1.3, and we have some techniques where people in Cambridge and in Imperial are now growing dots where, at least at room temperature, we've got the emission down at 1.55, and we're hoping to push the low temperature emission down to that wavelength pretty soon. So if you want to characterize a single photon source, then you just actually put it through a beam splitter, you do a Hamry-Brown twist experiment, look for coincidences. If you have a single photon that comes in here, then you get a click either here or there, so you get a very low count rate at the time zero. And this is a technique that's used quite widely in all sorts of experiments, from rubidium experiments of single atoms to ion trap experiments and so on, all over the world. So the trouble with quantum dots is that they are in a crystal. And if they're in a crystal, they obviously interact, therefore, with the crystal lattice. And so you've got interactions between this essential artificial atom and the surroundings, which are much, much more profound than you get with a single atom. If you have a single atom, it just sits there and, hopefully it doesn't interact with anything else. Whereas if you have a quantum dot, the phonons become a big issue. To get rid of the phonon problem, you have to cool the sample down. So most experiments on quantum dot systems run below 30 Kelvin. So you have to use liquid helium. So we've got a micro-PL system in the laboratory where we have a cryostat here, 100 times objective. We bring our light in, and then we actually put the emission onto our spectrograph. We have an indium gallium arsenide diode array here, and we have a confocal arrangement where here we can actually put the light into a fiber, and we can then pass that light from a fiber into a superconducting detector made by a Russian company called Skontel, which gives you about 200 picosecond time resolution at 1.55 microns. So we can actually detect single photons at 1.5 microns with about 30% quantum efficiency, which is not bad, okay? But they're quite fast. And also the noise count is very low, 1 or 2 counts per second. So these are very nice detectors. And unfortunately, the detector itself runs at liquid helium temperatures, so you have a second helium can in your room with your detector plunged into that. So there's an awful lot of helium going around to actually make this work. But for what we wanted to do with these photonic crystals, which I'll talk about in a moment, we needed to be able to excite the sample at one position and collect the luminescence from the sample at a different position, and then scan the excitation across the surface of the sample. So to do that, we set up a 4F system here, a telecentric system, where you have a piezo mirror down here, and as it actually changes its angle, you set it at a focal length f from this lens, so that the angle here turns into a focal spot in the focal plane. And as you change the angle here, you simply move the spot up and down this focal plane. If you then have another lens 2f away, then what will happen is it will actually recollimate the light and bring it back at an angle theta into the objective. The effect of this is that if this is the plane or the surface of your microscope objective, and this is your laser beam, you have a collimated beam which you can now do this with. And the effect of that is to actually scan the spot across the surface of your sample. Now, the luminescence coming back up through the objective comes through the center and is focused onto your detector. So you can collect light from the center of the objective, but you can actually excite the sample anywhere within a 50 by 50 micron range around that point. So we can excite and collect in different positions. So this is an example of the emission spectra we get from dot ensembles. You see they emit from about 1270 to about 1310 nanometers at 4 Kelvin. And we can get some quite nice sharp lines with about 2,000 up to 8,000 counts per second on our detector. So they're reasonably bright and they're quite easy to use. But of course the trouble with these things is they're entirely random and they emit into 4 pi. But it's worse than that, because in a semiconductor you've got a fairly high refractive index. And so if you imagine the light coming out from in 4 pi from your dot, when it hits the surface of the semiconductor, it refracts outwards. So only a cone of about 20 degrees of emission from the dot ever escapes. The rest gets trapped inside. So the efficiency for a bare dot in a bare semiconductor is very low. So you need some kind of cavity to actually improve the emission of the dot into free space. And that's where the whole field of cavity emission comes in. So just to prove that we can actually do this scanning, this is a piezo scanning of the objective, and this is scanning the mirror, and we can see we get a very similar set of data for the first and second order modes from our cavity from the two systems. That's just a proof that you can do it. So why put a dot in a cavity? Well, you can get into the strong coupling regime, or even the weak coupling regime. We don't care particularly which way one or the other. We'd like to get strong coupling. And what happens in strong coupling is, of course, that the emitter becomes coupled directly with the cavity, and so the cavity decay rate and the emitter decay rate become comparable. To do this, you need a cavity with a very small volume. And the trouble with normal cavities is they're rather big. So if you use real normal Fabrication cavities, even the tiny ones like I use for the biological stuff that I do, the volume of that is about a cubic micron. To actually get strong coupling with a quantum dot, you need the volume down to a cubic lambda. Okay, so that's much, much smaller, okay, inside the crystal. And so to do that, okay, so, and the lifetime of the cavity is determined by the width of the cavity. And so what normally happens is that for a strongly coupled cavity with a Q of about 10,000, the lifetime in the cavity is a couple of picoseconds. The normal lifetime of the quantum dot is of the order of a nanosecond. So you can go from 1,000 picoseconds down to 10 picoseconds when you couple the cavities together with a dot. So you get a strong reduction in the lifetime of the dot, and also actually a significant broadening in the dot line width, because the dots themselves are Lorentzian broadened, and so the natural line width of the dot is a few microelectron volts, whereas the typical cavity line width is a few hundreds of microelectron volts. So one of the signatures of strong coupling is that you cannot distinguish the difference between the cavity lifetime and the dot lifetime. And so what you see is, as you tune the dot into resonance with the cavity, the line width of the dot broadens to match the cavity, and so the two curves appear identical. So that's one of the crucial tests of strong coupling, is this line width change from the dot of 1 nanosecond to 1 picosecond. Much easier to do is to look at the Purcell factor. Here, of course, you're just using the cavity to enhance the spontaneous emission in the cavity from the dot. So if you enhance the spontaneous emission rate, then you reduce the lifetime. So here you can reduce the lifetime of the cavity of the dot by a factor of 2 or 3 or even 4. And so you can but it also increases the directionality. So as you perturb the emitted field of the dot into the cavity mode, that perturbation also changes the spontaneous emission, because you're using the cavity modes now to actually stimulate, if you like, the spontaneous emission, rather than the normal vacuum modes that would actually trigger a spontaneous emission event. And Purcell showed that for a two-level Lorentzian system, this depended upon lambda upon n cubed, where n is the refractive index of your cavity and lambda is the wavelength, the Q of the cavity, and the volume of the cavity, okay, and the Lorentzian curve here. And so the Purcell factor on resonance just depends upon 1 upon V and on Q, so it's Q upon V. And it's much easier to do that, to actually get this to actually work in a dot system. On the other hand, and you can see this, so this was first done in France, and they used an etched pillar with quantum dots in there with a Bragg reflecting mirror at the bottom, and they actually got a lifetime enhancement here of about a factor of 5, I think, or 4 or 5. So you see it got much faster in the decay from the dot as they coupled the dot into the micropillar cavity. So, and also, of course, what happened was the emission now came out in a lobe, sort of in this sort of shape, from the top of here, rather than emitting in all 4 pi. So now they knew where the light was coming out. So their collection efficiency was very much higher. And that's one of the reasons I want to do this. Because clearly, if you had a device now which is built on these things, when you connected, say, a P junction up here and an N junction down there, and you passed the current through it, then you'd know exactly where your single photons are coming out, and you could collect them by putting a lens above your nanorod. So it's a nice way of collecting the photons as well. It's not just a matter of knowing where the photons are coming out, but you need to know when they're going to come out, and you need to trigger them. So the whole point of this, the holy grail, if you like, for the semiconductor industry here, is to make a triggerable single photon source. You can even make a photon pair source, because a quantum dot has an exciton state and a biexciton state. So you've got 2 levels, and the biexciton creates a cascade where the photons go in 2 directions. And so if the 2 energy levels they can decay to are resonant, then you can't tell, you have no which path information, and so you get an entangled pair of photons that comes out from your biexciton. So you can actually create a pair source, and Toshiba have done this already for a bare quantum dot in the system. Okay, so in the strong coupling regime then, you get these dress states, and more importantly, the splitting, the vacuum Rabi splitting you get depends upon the square root of the volume at the bottom here. So if you can make the volume very, very small for your cavity, you can actually get into the strong coupling regime. So what you want to do is to make an optical cavity which is as small as possible. So that's the whole point I'm trying to get at here, why we're bothering to use photonic crystals. Okay? And the enhancement that you get just depends on the alignments of the cavities and the coupling constant. And in the weak coupling regime, you just get irreversible energy transfer, control the spontaneous emission, but it depends on Q upon V. And in the strong coupling regime, you cannot tell the difference between the dot emission and the cavity emission. The spontaneous spectrum is split. You get an anti-crossing, and so as your dot is tuned into your cavity, instead of actually crossing like this, you get an anti-crossing, and the anti-crossing, the size of the anti-crossing is the Rabi splitting that you actually get in the system, and that tells you how strongly coupled the system is. And the average line that you get is simply that of the dot plus the cavity divided by 2. And remember I told you earlier on that the dot line width is very small, so it's dominated by the cavity line width. So the dot broadens, the dot line width broadens into the cavity. And the important point here, though, is that it depends on Q upon root V, and that's the essential thing to bring out of this discussion. So a very small mode volume is needed to actually get strong coupling, whereas you can get away with a bigger mode volume to get Purcell effect. So you can see the Purcell effect much more easily than you can strong coupling in a semiconductor system. So here's an example of things that are actually been tried by various groups over the world over the last, let's say, 20 years. Obviously, this is what the atomic physics people do a lot when they want to put their atoms in a cavity. This doesn't really work with a semiconductor quantum dot in a crystal because, of course, the dot's embedded in the crystal. You can do this with single crystals, these things like cadmium selenide quantum dots. And in fact, Jason Smith, a colleague of mine in Oxford, has made some Purcell measurements. He's had a Purcell effect enhancement of 5 with an actual open cavity, a hemispherical cavity, using about a half a micron sized cavity. And we collaborated with him on this in a project. So micropillars, you can do this, but it's very hard to do because, first of all, you could grow a sample with very, very good dBrs. That's a growth challenge. You have to grow many, many layers, each of which is lambda by 4 thick. And lambda by 4 is very thick for an MBE grower to grow. It takes forever. It's very expensive. Your samples cost thousands and thousands and thousands of pounds to get to a decent cavity. And if you get it wrong, you throw it away and start again. So it's actually a very expensive problem to actually get good samples. And then you have to use reactive ion etching to actually get perfectly good pillars. And you actually have to find a dot in the micropillar that actually works. Nonetheless, you can actually get a vacuum Rabi splitting which is quite high, 140 micro EV, whereas the photonic crystals you get about 170. And the micro disk you can get 400. Micro disks are very easy. You use Wisping gallery modes. The trouble with that is the emission is sideways. So you get perfectly good cavities, but the light's going the wrong way. It's going sideways rather than out of the system. The advantage of both this system and this system is the light leaks out vertically, and so you can collect the light in a mode in a nice shape, a nice lobe shape, which I'll show you in a moment. So then, let's take about photonic crystals. Why bother with photonic crystals? Well, the real reason you want to do this is that the lattice parameter is quite small. In a semiconductor, it's about 100 nanometers or so, because of the refractive index. And so you can actually get very small mode volumes in your system. So why do they work? Why does a photonic crystal behave just like a crystal? Okay? If you do any standard undergraduate physics course where you look at condensed matter physics, you will do band theory. And in band theory, you discover Bloch's theorem that tells you that if you actually have a periodic potential in your crystal, that periodic potential will actually break up the continuous solutions to Schrödinger's equation into bands. and you will get band gaps. There'll be regions where plane waves do not propagate because of the periodic nature of your crystal, particularly when your wavelength gets of the order of twice the lattice spacing. So how can you actually turn a bunch of holes, or a bunch of pillars, if you like, in a physical crystal into a photonic crystal? Well, the answer is, of course, the electric field and the magnetic field in an EM wave is already a nice set of plane waves. Okay, so you've got a perfectly good plane wave anyway. Fourier theory says you can always decouple the system into plane waves. The things will scatter coherently when lambda is of the order of 2a, and you'll get, therefore, a photonic band gap formed at that wavelength, as long as you can make Maxwell's equations look a bit like Schrödinger's equation. Because Bloch's theorem strictly applies to Schrödinger's equation. Well, the answer is you can. You can actually recast the ordinary Maxwell equations here for free space into these equations here. So if you just take the curl of both of these, then you actually get curl H is omega squared mu naught h, and that looks like an eigenoperator operating on a wave function, give you with an eigenvalue and an eigenstate. So you can recast Maxwell's equations to look just like Schrödinger's equation. It's not quite the same, but it sort of has the same effect. And what it means is you actually will get Bloch-like solutions to the propagation of the electric field. So the magnetic field and electric field will now propagate like a plane wave plus a periodic envelope, just like you get for the periodic envelope for a normal crystal, which actually has the periodicity of the crystal built in, and therefore these Bragg-like reflections when lambda is of the order of 2a. So case conserved, you get no scattering, but you have a discrete set of frequencies, and the point of what this is now, it's broken up into n bands. So you now have a discrete set of solutions, not a continuous set of solutions for your frequencies. And that's the important point. So you can then do exactly the same kind of band structure calculations that people have been doing since the 1930s in crystals, except that you use a finite time difference calculation method where you solve the equation for the electric and magnetic fields in a small cell, and you match it to the next cell and the next cell, which is extremely computer intensive, but in principle very straightforward. And what you find is that for a two-dimensional slab, those are holes and those are rods, what you discover, you only get a gap in either the transverse magnetic mode or the transverse electric mode. You don't get a full band gap. You only get a band gap in one of the two modes. To get a full band gap, you need a three-dimensional photonic crystal. And the trouble with making those is quite hard. You need to do something sort of holographic, and it's not straightforward at all. There's a lot of groups in Japan working on that, but in fact, you don't need to do that because you can use a thin slab, as we do, to give you a quasi-third dimension. So that's what we do here. So now we have a finite thickness here. So you have a thin slab with holes in it. It's a hexagonal crystal. And what you discover is that where omega equals ck, which is these curves here, that's your light curve. That's your frequency of light against the wave vector. The light can leak out into the space, but you get regions here where you've got no emission. But the trouble is, you don't want light to leak out sideways. You want light to come out in a mode that's perpendicular to the cavity, to the slab, in some well-defined position spatially, so you know where the light's going to come out. And so the answer to that is to do what you do in a normal crystal. In a normal crystal, okay, which is once you allow the crystal to not be perfect any longer, you put a defect in. You put a defect into a normal crystal, what you do is you create a state in the gap. That state in the gap from a perfect crystal now has no dispersion. Okay, it's a fixed position, and it has a fixed energy. So in a three-dimensional crystal, it'll just be a line, a band, an energy level. And here, what you'll do is you'll create, and you do that by creating a missing hole. So it's very simple. You write your pattern. I'll show you how to do it in a minute, and you just miss out a hole. If you miss out a hole, you get a state in the band gap. So now you've got this state here, which is isolated at a given frequency, okay, and the field decays away in some way relative to the central frequency in a sort of nice sort of Gaussian or Lorentzian type of fashion. And so when you create this defect here, the light can leak out at these points here into the light cone, and you get emission vertically out of the cavity as opposed to light being trapped inside the photonic crystal. So now you have light everything up and down, of course, because it goes both ways. You can't stop it going both ways. It comes out from the top and bottom of your slab. The trouble with doing this is, if you actually simply miss out a hole, or in this case 3 holes, because it turns out to be the best thing to do, then you get a very sharp transition between hole, no hole, no hole, no hole, hole. Now, if you think about Fourier theory for a second, anything sharp is a bad idea. Because if you have anything sharp in space, then in frequency space, that thing's going to have lots of frequency components, right? So what you get is a lot of ringing for your leaky regions. And so you get lots and lots of frequencies. What was discovered by Akahane and people in Nature in 2004 was, instead of actually having this hole and a missing hole, you shift this little hole a little bit this way, and you shift this hole this way a little bit. And it has the same effect as what astronomers have been doing for years, and also spectroscopy, people with gratings, it's a thing called apodizing. Basically, when you apodize, you put a Fourier transform filter across your diffracting element of some shape. You can put a Gaussian one or whatever. And what that does is actually reduces the spatial frequencies at the sacrificing a little bit in resolution. And the reason you want to do it as an astronomer is, if you have all this ringing, for instance down here, and you were trying to look at a bright star against a very dim star, then if the dim star happened to be there, you'd never see it because it would be on the bright ring of the other star. If you actually do this, where you end up with a Gaussian type shape, you could have a very small star flipping up here. You could see it very easily. So you'd be willing to sacrifice a bit of resolution to actually give you contrast. And that's what you do. So by shifting these holes, you get these very nice cavity modes, which are sort of Gaussian in shape. And I hope this works. So let's see if I can get this to work. So this is a model that was done by Kevin Hennessy at Santa Barbara, using finite time difference simulations to show how the light emits. So basically, these are the electric field amplitudes in the slab. Here's the slab. These are the holes. It's an L3 cavity. There are 3 missing holes. And it should... there you go. It works. So you see, the light is emitted this way and this way. This is your light field now. These are the EM waves coming out. Some leaks this way, but most of it comes up and down. So most of the light leaking out from your cavity comes out vertically. You can also do it from the top. So this is now the same calculation, but now looking down at the top of the slab. Here's the central hole of the 3 missing holes. These are, again, the electric fields. And if I run it, you can see it just pulses. There's your sine wave essentially coming out vertically out of here in this direction. So out comes a very nice beam. So you put your microscope objective above here. More importantly, you can put your quantum dot right there. So if you can put a quantum dot at the center of this field, the actual cavity volume is the size of that little spot there. And that is about 100 nanometers, 200 nanometers. So your root V is tiny. So you get Q upon root V, that is very big. So you get a chance to get strong coupling in your cavity by using this very small mode. So how do we do it? Well, the fabrication is done. You grow your sample with on bit of gallium arsenide. You grow a layer of aluminium gallium arsenide with a high aluminium content. Then you grow more gallium arsenide. You grow a layer of quantum dots, and then another layer of gallium arsenide. This stuff here can be etched away. What you do is you put a mask on, use an E-beam machine to write patterns over your surface. When you develop that pattern and then etch with the reactive ion etching, you actually end up with holes through the system. You then pass hydrogen fluoride over the sample. It etches away the aluminium gallium arsenide, but not the gallium arsenide. And you're left with an undercut region here, where you've got a slab underneath, on top, and an undercut region. What you do is you actually make little rectangles around the side to let the HF leach in, etch underneath, and wash out. So you wash out the HF afterwards. I have to say, I don't do the HF etching myself. I got somebody else who does that for me in Cambridge, and they wear these sort of suits with masks and all sorts of things, but hey, that's not my problem. But you end up with a very nice system. If you're not careful though, if you have a poor reactive ion etching system, you end up with this kind of problem. You see here, you end up with a cavity which has now got the edges aren't straight. And that affects the Q value of your system. So instead of having 100,000 Q, which you can get typically in these systems, you end up with a few thousand. So it's a big problem if you don't have good etching. So you have to have very good processing. And that's why we collaborate with Cambridge, because in Cambridge at the moment they have a Leica e-beam machine, which is actually serviced by a Leica engineer who actually developed the machine. And he runs it now, because when Leica moved their headquarters for research into America from Cambridge, he didn't want to move. He was happy there with his family. And so Cambridge employed him to run their e-beam machine. So now they have an expert running their e-beam machine, and he can set it up perfectly, so he can know things like proximity effects, which are due to electrons from one hole making the other hole different shape, and so on. So he can produce beautiful patterns. I mean, he really is almost a magician. So you just give him the pattern, the AutoCAD file, and 2 weeks later comes back your pattern sample all working perfectly. It's very nice, as long as he's still there, of course. But anyway, it works very well. So let's look at what we can do with strong coupling. So a few years ago, we did this just in a single cavity to show we could do strong coupling with a single cavity. And this is where you tune the emission of the dot through the cavity mode by changing the temperature of the crystal. The dot shifts, the energy of the dot shifts because of the band gap of the actual crystal changing, because the crystal expands and contracts, and that affects the coupling of the band structure, so the dot will shift. Whereas the gross structure of the photonic crystal doesn't expand and contract so much, and so the photonic crystal mode doesn't move very much at all. So what happens is the uncoupled cavity shifts a little bit with temperature, but the dot shifts a lot. And if there was no coupling, you'd just get one going this way, one going this way. But what actually happens is you get this anti-crossing, and this separation here is a measure of the Rabi splitting in the system. You can see it here, and here's the quantum dot. Now I hope you can notice the quantum dot is narrower, but at this point the two are the same width, and up here you can see it better there. The cavity is much wider than the dot here. Here they're the same width, and again the cavity is wider than the dot down here. So at this point you've got the anti-crossing, and you've got the strong coupling because the two are the same width. That is the real signature, the fact that the two line widths have become identical. If that hadn't happened, then this would not be strong coupling. Even if you saw anti-crossing, it would still not be a strong coupling. And so some people have published papers where they say they've had strong coupling, but they haven't seen this line width shift, so they haven't actually got it. Okay? So it's quite important to have both things. You need the anti-crossing and the change in line width to get the strong coupling. Okay, so how do we actually make this thing? Well, we want to do this with a waveguide, because the point about this is just having a single photon source in a single point, it's all very well, but if you want to do anything, you want to actually control the emission. You want to make entangled pairs, you want to block photons, you can do all sorts of clever things if you can actually have more than one of these sources. And the point about this is you can now use a new system rather than the L3 cavity, and this is a photonic crystal waveguide. And the reason this is important is that the light is now confined within the waveguide by the band gap of the crystal. So not only can it emit vertically, but it can also emit along the waveguide. And you can suppress the vertical emission if you want to, so you can actually get only waveguide emission. So you can get, now you can actually put a series of these together. And this was done by Notomi in 2008 in silicon. So in silicon it's much easier, because processing in silicon is very, very mature. And silicon is a very nice material to drill holes in. Okay, so people have been doing it for many, many years. So you can get very, very high Qs. And he actually made a slow light cavity, actually, was he was doing here. He was actually putting a whole bunch of these together and then sending light down through the cavity. And the dispersion of the cavity was such that he slowed the light down by factors of 10 million or something, some incredible amount in this system. But what we discovered was we could use this also to produce cavity modes. What you do is this. You make a waveguide cavity, you simply have a hexagonal periodic array of holes up here and a hexagonal array of holes down there. Then what you do is, here you shift these two holes by a little bit, these holes by a little bit less, and those holes by even less. So by shifting the holes by different amounts, what you do is you create an optical well here. It's essentially the equivalent in optical terms of a standard particle in a box, which is quite nice because you can do all the quantum mechanics for that very easily. So it's like a particle in a box. You create an optical well here, and what happens is your photonic crystal band moves up. You get a cavity mode which essentially sits at the light cone. You get emission here, and it looks like that. So it's very similar to an L3 cavity, but you have now got full control over the system. So here's the kind of dot cavity mode. So you see at 1300 nanometers, we've got 10,000 Q from our cavity, and we can actually couple it to these dots. So that works quite nicely. We can also actually do the scan along the system. So here's what our dots, our photon spot size is like, if you like, because diffraction limits you to about 0.8 microns with a normal objective. 100 times objective, the smallest spot size you're going to get is about 0.8 microns at 800 nanometers. And that's our exciting wavelength. And so you can scan this across that's the whole photonic crystal. And if you have no cavity, you just get the waveguide emission and a suppression here. See, the light is suppressed here, and then here's the waveguide emission. But if we actually then look at one where there is a shifted set of holes, you see you get a very nice Gaussian-shaped peak in here. Well, actually, it's a Bessel function. It's just your diffraction from a circle shape, and here is your the emission from the dot coupled to the cavity. And the way you do this very easily is you make a high density dot sample. If you have a high density dot sample, you can guarantee that every time there will be a dot where your cavity is. So while you're developing your cavity system, you do it with high density. Then when you've got it all worked out, you go to a low density sample system, and then you register where the dots are, which we've done in the past. And you do that by actually measuring where the dot is, and then putting markers down optically away from the dot, which the E-beam people use for registration. So when they register their system, they actually use a registration point marker. They use these then as registrations to write their photonic crystal. So we can do that. We can put the cavities where we want, where there's a dot. We've done that in the past. That's all sorted. So what we want to do now, so this is really what the thrust of my talk. So far I've talked about single photon emitters and single cavities. But actually what you want to do is to have molecules, photonic molecules. And the reason for that is there are a whole bunch of things you can then do quantum mechanically using one cavity or the other, because you can block the emission from one cavity by shifting the energy in another cavity and so on. So you can do things like what's called a photon turnstile, where the dot would like to couple to this cavity and emits here, but you stop it, you frustrate it, and so it sticks in here and it's trapped in this cavity until you release it with an electric field, say. So you put an electric field across the cavity, and suddenly you can pop out a photon every time you put an electric field on. So you can pre-populate the cavity and then trigger it, and out comes a photon when you want it. So you get a triggerable single photon source in the infrared. But to do that, you have to control the coupling strength between your two cavities. So how do you do that? So one way of doing it is what was done by the French. Again, this is Douce in 2010 in Nature. What they did was they actually made two of these vertical cavities they'd been working on, and they simply made them coalesce. You can see that actually there's almost like two vertical cavities here joined at the hip, so to speak. And so there they couldn't control anything. They just had by chance they could see the coupling, and they actually got coupled supermodes. Here's a theory experiment which says you can actually get anti-bunching from quantum interference by actually having an empty cavity with control by a light field and the quantum dot. So you can use the light field itself to actually trigger the emission from the dot or not. So you can use the cavity coupling to actually trigger emission from the dot. So how do two cavities couple? Well, of course, it actually turns out to be exactly the same problem as any quantum mechanical coupling problem. It doesn't matter whether it's a hydrogen molecule or a photonic molecule or anything else. Okay? Any set of systems which you can couple, where the solution for the system will have two solutions generally for the first excited state. You'll have a symmetric solution and an anti-symmetric solution. It happens in hydrogen. Okay? It's called, if you do hydrogen in chemistry, it's the bonding and anti-bonding solutions to Schrödinger's equation for a hydrogen molecule. Exactly the same. There's no difference. And so you get a phase term And that term is dependent on the coupling strength J between the system. And you get a splitting, okay, here, and a coupling. So there's the coupling. The coupling depends on the splitting and on the coupling strength. And the splitting is just the difference in wavelength between the two emission peaks. So this was first demonstrated in a semiconductor system by Bayer in 1998. And he used the quantum well sample. And he made a quantum well sample where he created essentially a bridge between two slabs of quantum wells. And he calculated that this could actually look just like the analogy to a hydrogen molecule for the excitons in his system. So what he said was, these look like hydrogen molecule orbitals. You have bonding and anti-bonding. You can see you've got the first and second steady states here. You've got the two are adding. So you get some emission you get some field in the center here. If they're antibonding, you get nothing in the center. So you've got almost no field at all in the center between them. So you've got repulsion there, but here you've got an overlap. This is like essentially a sigma bond in a carbon system. Okay, and that's like a P system. So what they did, because they were making this lithographically, they could actually change the width of the bridge between the two systems, and they could change the length of the bridge. In other words, they had two levers that they could pull to actually control the coupling between the two slabs of quantum well that they had. So what could they do with that? Well, it turns out that the splitting depended on J, and J was controlled by the length, whereas the tuning was also controlled by W, the width. So as they looked at the symmetric and antisymmetric modes, they looked at the splitting, they discovered that if they changed the length from 0 to 4 microns, they got a very, very small splitting, which was fairly symmetric, and they didn't have much control over it. Whereas when they actually changed the width, keeping the length fixed, one of the modes, the antisymmetric mode, didn't disperse very much, but the symmetric mode dispersed a lot. So they had more control now on the coupling between their system by changing the width of their coupling mode rather than the separation. Now this is important because we're now going to do an exact analogy of this with our photonic crystals. Okay? So here's the photonic crystal version that we've been doing. If you have one of these cavities, just one cavity, then obviously you'll have a first order mode and you have a second order mode. And you'll get a splitting of about 10 nanometers for the second order mode. If you have two of these cavities joined together, here, written very close to each other, then what you discover is they will couple, and you'll now get a symmetric bonding mode, which you see is much bigger. Can you see look at the extent? This is a theoretical calculation, but here's the width of this one, and this one's much wider, because now you've got this hydrogen-like sigma bond type thing. You've got a much broader coupling between the system, and equally you've got your anti-bonding system. The peaks are much closer together. And so they're also closer together in wavelength. The splitting is only about 4 nanometers instead of 10 for the second order mode. So you can tell the difference between the first order and second order mode by mapping the shape of these things. And I'll show you that in a moment. So we can see that here. So here's a single cavity. So this is experimental scan over the emission from the cavity. First order, second order. And you can see we can actually resolve, if we deconvolute out the resolution of the actual microscope objective, you can see it actually the theory and the experiment match very well. And here's what happens when you have a couple cavity. You see this is much wider, and these are actually much better resolved, and you've got the antisymmetric mode with a smaller splitting. We were a bit disappointed, though, that this wasn't a flat top. Can you see it actually it's got a sort of rather funny shaped sort of edge? It turns out this is down to this super guy in Cambridge making a mistake. He thought his system writes patterns by writing by interleaving the spots. So he writes one pattern and then another pattern. And what they hadn't realized was that there was a slight glitch in his software, and what happened was when they wrote the second pattern, there was a systematic shift of the second pattern by about 2 nanometers from the first pattern. So what he actually had was 2 interlocking lattices slightly shifted, and the effect of that was to make an error in the cavity mode. So in fact, we actually fixed his system for him by showing him that the system was actually inaccurate. Because you couldn't see a shifter that small but in actual SEM measurements. But we could actually detect that from the coupling of our system. So he then fixed it. So then we had flat ones. So we now have flat ones. So he's fixed the system from that point of view. So here's another one which is fixed. It's much flatter, this one. It's broader. And here are the modes again. And you can see the symmetric mode. See how flat this is now? And you can see it's much wider. So that's the theory, that's the experiment. And you can see again the splitting is much bigger for the single cavity than it is for the couple cavity. So we can actually make photonic molecules. But then we've still got this problem. Remember, going back to the picture we had before, you've got this question, how do you then control the splitting? Well, some people decided to do this by actually having L3 cavities like these and adjusting their relative separation at an angle. And when we tried doing it by moving these by fixed number of lattice spacings. And the problem you've got is this. If you actually just change L in that earlier problem, the length, you can only do it digitally. You can do it one period at a time. You can't do anything else. All you can do is move one hole or two holes or three holes. So this is actually happens to be 6 holes apart. That's a 6A splitting. And what you discovered was we have a very, very small splitting in this case between the symmetric and antisymmetric mode when we go that far apart. And also we couldn't tune it finely. We couldn't choose our J. And to do anything sophisticated with the system, we have to be able to choose our coupling very accurately. So just shifting these things sideways, it worked, but we couldn't do anything with it. It was no good to us. So we then thought, okay, well, how do we do the same thing that they did, which is just change the width? What's the equivalent in our system of changing the width? And the answer is to put in an intermediate well, an intermediate barrier or well. Then theoretically, these are the calculations, you can now get, for this 2-hole barrier, a continuous change as you shift the hole displacements in this well. So how do you make this little barrier or well between our two cavities? Well, the answer is in the same way as we actually get around this problem of the apodization. You shift these 3 holes vertically, and you shift these 3 holes vertically away from the periodic center. You then create effectively a well between the 2 cavities, and here's now the experimental data. As you can see, we have effectively arbitrary hole shift because the point is where these holes are is determined entirely by the E-beam. So you can write the E-beam position anywhere within the resolution of the E-beam, which is about 8 nanometers. So within 8 nanometers, we can actually write the central position anywhere. So we can control this shift very accurately compared to the periodicity, which is about 100 nanometers. And so you see we've got now continuous shift in our whole system. People, Atlasov tried to do this in 2008 by changing the size of the hole. But the problem he had in doing that is that as you make the hole bigger, the etching changes. And so you have, smaller. So big hole is easy, small hole is very hard. Because you just can't make a small enough hole. You simply can't get the hydrogen fluoride to etch properly or the RIE to etch properly through a small hole. Whereas this way, all you're doing is keeping everything constant. The only thing you're doing is shifting them, which is entirely in your control. So we've now got this working, and we published this in Optics Express last year. We can actually map that, and one of the things you can see is whether the kind of energies that you see in this system correspond to the theoretical models. And one of the things you discover, first of all, is that you should get a 3rd peak in the second symmetric mode. And you see that here, you get three bumps. It shows better, I think, on the next one. Yes, here you go. So you see, you get 3 bumps for the second symmetric mode. So here's the first symmetric, first antisymmetric, second symmetric, second antisymmetric. And you can see here you get 3 peaks. And as you shift the distance, they shift and change in a very predictable way, which actually matches perfectly with the modeling. So we have a full control on the modeling and on the energy of the system. That's the difference in the experiment and theory. And there now is our coupling fine-tuning against hole shift. So we can control the coupling between our molecules and therefore control this the energy. So the next stage, which we're working on at the moment, is to put these to the test in a low density sample, where we have a very low density of dots, and we have a single dot coupled to a single cavity. It's much more challenging to do that, but we are working on it as we speak. Okay, I'll skip this bit. The other thing that's interesting we discovered was if you make huge shifts, you also get a sort of a nice splitting between the single cavity and the multiple cavities. And so we're trying to exploit this because by the time you could do 18 separations, we thought you wouldn't have any coupling at all. You know, you've got 18 periods apart. These things are miles away. And yet, they still see each other. They can still couple. And so you still get a resonance between these molecules. And actually, it's much easier to make something that's 18 periods apart than it is 2 or 3. So we are thinking about exploiting this in a clever way. You could, if you had a very fast detector, actually see the light being sloshing back and forth, because what's happening in these coupled cavities is the light is actually going back and forth between the two molecules. So it's either on this one, or it's on that one, or it's on this one, or it's on that one, and so it's emitting back and forth. But unfortunately, the beating period is about 1 picosecond, or even, or for this one, half a picosecond. And there is no detector at the moment that's fast enough with single photon sensitivity to see that. So you're only ever going to see the average, the time average, unfortunately. So we only see the time average emission. We can't see the individual speeds. So to finish then, some new work is just, as I say, just being about to be submitted to the conference this summer. We thought, hang on a minute, it's much easier to make 400 or 1,000 identical waveguides with no shifts. In other words, just make waveguides. And then try and make the cavities directly with a laser beam having found the dot. In other words, cut out the whole phase of the production process. And the way you do this is by putting a disk of SU8, which is a photoresist, down on the system. So negative resist, so when you expose it, it actually stays there when you develop it, and everything else is washed away. And so what we discovered was we modeled the effect of basically a little slab of dielectric sitting above one of these photonic crystals to see what effect it had on the emission of the cavity. And surprisingly enough, you get a cavity. Just by putting a little bit of essentially glass, if you like, a little blob of something transparent above the OR system, you get a very nice cavity mode formed. This is a 1 micron diameter, 50 nanometer thick slab. This is a 100 nanometer thick slab, 2 micron diameter. You get very nice cavity modes. The only difference is, for the very thin layer with a very small spot, you get a high Q, and for the thick layer with a bigger spot, you get a lower Q. But you can control the mode volume very accurately, and you can actually control the emission energy by choosing the material refractive index. And it turns out SU8 is very good for this, and it matches our dot emission very nicely. So we tried this, and this is our first result, and it's actually worked. So here is a blob of SU8 written exposed by a 2-photon process. So SU8 absorbs in the blue. We use 800 nanometers, femtosecond pulses, and use the 2-photon absorption. That way we can excite the sample without actually at low power and find the dot. Then turn the power, shut the shutter, turn the power up, do a quick shot to expose the SU8, shut the shutter again, and that creates a little blob of exposed SU8, which we then develop. And this is an AFM picture, and this is the micro-PL scan of the same thing. This is actually a straight AFM, so these holes you see in the AFM. This is actually a montage of an SEM image and our micro-PL image. And here we have a cavity of 2,300 Q. And given that this actually is about 200 nanometers high and about 2 microns across, it matches almost perfectly with the theoretical model. So my graduate student is now beavering away happily, trying to thin the solution of the SU8, the viscosity, such that he can spin it with, instead of a thickness of 200 nanometers, with a thickness of 100 or 50 nanometers, and then repeat this experiment, and the Q should go up then from 2,300 to more like 20,000, which is what we need. We're not trying here for strong coupling, we're just using this as a Purcell source to try and improve the emission. Because this way we can actually do very nice things, like for instance, once you've got one, you can actually write n of them. Because all you do is you move along the cavity with your micro-PL system and just write more and more, and you can make a whole chain of these things all in one go. And it's just a matter of developing it. It's a very quick thing to do. So we're hoping to work on that, and as I said, the student's working on that as we speak, and his results so far are looking very good. One person objected and said, well, if you just hit the thing with a laser pulse that intense, you might be actually damaging the crystal and creating a cavity just by damaging it with your laser, and nothing to do with the SU8 at all. So we thought, oh, we better test that. So he's just done an experiment where he has no SU8 and done everything else exactly the same way, and he doesn't get any effect at all. So it does prove that it really is the SU8 that's doing the cavity formation. And so we do need to have the blob there. It's not some sort of laser burning effect. So we've now proven that. And so he's working on that at the moment. Okay, so to conclude, we can now write photonic crystal molecules, control the splitting between them. We can do it with high density dot samples very easily. We have full control of the processing. So we're now moving to the final stage of the project, which is to actually do it with a single dot, which is the challenging part. But if we can do that, then we can actually produce a triggered single photon source at telecom wavelengths, albeit, I'm afraid, at 30 Kelvin. So you still have to cool it down. There are some hopes with different material systems. We're working on the nitrides, where we've already got a single photon emitter at 200 Kelvin. And if we can, the trouble with doing that there is in the blue, this whole thing scales like lambda upon n. And so if lambda gets smaller, then your volume has to get smaller, your features get smaller, and so the writing of your e-beam system has to get more accurate. The advantage of going to telecom wavelengths is that your R upon A, the radius against the separation, it stays constant, but it scales with a wavelength. So if you go from the people who did this at 800 nanometers, where we did it first of all, to doing it at 1500 nanometers, you actually have 4 times better Q instantly. Because if your roughness stays the same, the roughness of your hole, and if the accuracy stays the same, and you make everything twice as big, because it scales as the width and the roughness, you actually get 4 times better Q for doing nothing, apart from making the wavelength twice as long. So you win hugely by going from 800 nanometers to 1500 nanometers in the whole thing. Everything's easier as you go redder. Conversely, you go bluer, it gets much harder. So that's a problem. Okay, thanks very much.
I'm just a little concerned, Robert, that you said your student is working on this right now. It's 5 a.m.
Oh, well, no, he's probably not working at this very minute. He's probably asleep. Although he does keep very strange hours, I have to say. He likes working at night.
Any questions?
Just a quick one. I mean,
Yeah.
in your last result, you had the SU8 blob, and then in the AFM is very, I mean, it's not symmetric over your waveguide.
No.
So if you get it more symmetric, your
Q should be a bit better, yes. But actually, it turns out we did some modeling. So one of the things we did was to work out how close does it have to be. And because of the evanescent fields in the system, it turns out it doesn't have to be that accurate. So a shift of maybe even 30% off center doesn't have much effect because the fields penetrate. It's because lambda is large, it's actually in the air. So actually, it's a very forgiving technique. Now, what really kills you is the thickness of the SU8. So in the modeling, it's quite critical. The thinner you can make the SU8, the better will be the Q. And so it's far more important to get the thickness right than it is to get the positioning right. The positioning is, if you like, a second order problem, whereas the thickness is a first order problem. Eventually that accuracy will matter, but we can do it better. So we've got that. So we tried this with even thicker SU8, and we did a range of about 20 measurements, and I think in 10 of those 20 measurements it was perfect on the center. It's just that when you do the exposure, sometimes the thing drifts a little bit, and just for that particular one it's drifted a bit more. But we have a scattered range. But really, as I say, what really matters, and why the students now working on the thickness, is that the thickness is crucial in getting the Q right.
Just to the same experiment. So how about V in that cavity? So Q is a few thousand, you said, but V, do you compromise V?
So V compromise V a bit, yes. So the effective V is about twice as big as it is in the normal photonic crystal. So with a factor of 4 in root V. If, you know, it is a bit worse, but it's still tiny, so still very good. But see, in this case, we're not going for strong coupling. We're going for Purcell effect, and that scales as Q upon V anyway, so that's fine. So we just want enhancement of emission in this case.
In your measurement of the Rabi splitting in the photonic crystal cavity, how have you identified the two peaks? Which peak are the quantum dot or the mode?
Oh, just from the fact that you get anti-crossing. So you know, you just follow them. You know where they start off at one end. You know where they end up because the one is wider than the other. If that's one good thing about having one cavity, the cavity will be much wider than the dot. Away from resonance, it's quite clear which is the dot and which is the cavity on both sides, and then you just follow it, and then you can see. Because when they become identical, of course, they are identical. But you can fit them with a Gaussian quite easily. I mean, the splitting is much bigger than the width. So we got 140 microvolts, which is one of the best splittings, I think, for that system.
Okay. So have you tried any cavity with the lower volume? For example, use the air slot or the surface plasma polariton?
Yes. So we haven't tried that. I have a friend who's doing some work with surface plasmons. It depends what you want to do. As I say, if you just want the Purcell effect, you can actually get away with a slightly bigger mode, and it's much easier. So that's why with the SU8, we're not really pushing for a very small mode volume. We just want a good Q. So it depends. It's horses for courses. Strong coupling is very hard to do. Weak coupling is much easier. So you've got to try and think of a system which uses the benefit of one or the other. And so, you know. Christoph?
Yeah, so I had two questions. So the first one about, so you use SU8, so
yes.
What about, so SU8 is about 1.5, is about glass, the index, I guess?
Yes, that's right, yes.
So what happens if you take, like, I don't know, titanium oxide or some...
Okay, so we could use, okay, so we can model it, obviously. The thing is we need to have something that's 2 photon. You can do it a different way. So what the French group that did the pillar thing did was they actually set up a system where they had both green and red go to the same objective, and they spent an awful long time, I've talked to them about this, getting it perfect, so that the green spot and the red spot were in the same place. Once you've done that, you can then do positive resists as well as negative resists, and you can do single photon exposures. So then any resist you like that's transparent can be used to write the pattern. We just happen to use SU8 because we know it works with 2 photon, and we've got experience with it in the past. It's how we do the registration. We use SU8 for for doing the registration marks, and so we had a good feel for the 2 photon intensities required, and we know that you don't have to put too much power on. One thing you do discover, if you put too much power on your sample for too long, you anneal the dot. If you anneal the dot, you destroy its luminescence. So you can't, these exposures are of the order of half a second maximum. So it really literally is, and it's done. If you just let it sit there with 10 milliwatts or something, then it'll warm up. You'll warm up your system. You can't do that. So you have to have something that's exposed quickly. But yes, we could look at a different material. Yeah, absolutely.
And sorry, the second question I had, so regarding the 2 cavities, so you said that even when they're far apart, they still talk, right?
Yeah.
So, yeah, you said you have some ideas. So this is, I don't know, I think they call it frequency pooling or some, so, so have you looked into so in this case, they were about the same cavities, I'm assuming?
Yes.
But what happens if one is stronger than the other one?
Yes, exactly.
Right?
So that's the idea. So the thing to do is to try making them different. The problem is time and money. Money particularly, because the way the e-beam system works is you pay to have it done, but also there's a queue. Other people are trying to use the same system for other things, right? Not just photonic crystals. So there's a 6-week waiting list mostly for getting a system turned over. So you have to be very sure that what you're doing, A, is worth the cost, and B, is worth the time. And so we're just trying to do the things to be honest, it's a terrible thing to say, but we're doing what we were funded to do, in the sense that we have to produce for the funding agency in Britain the results that we said we would try. Once we've done that, we can become more exotic and possibly try some different things. But at the moment, we've done 2/3 of what we said we'd do. We've got the last bit to do, which is we've only got 6 months on this project left funding. So we really have to get the low density stuff done. So we had to switch to that. I think there are more interesting things we could do with the high density sample. You're right, but there's only so much time and money.
So you're, one of the reasons for you to get into the strong coupling regime is because your quantum dots are buried inside your cavity.
Yes.
So you have a very strong cavity field at the region of your
yes.
quantum dots, so this intersection is very high.
Yeah.
Say, in this scenario when the quantum dots are different materials, say you bring it from outside,
yeah.
And then are there any good ways to be able to realize a strong coupling?
That's hard. As I say, we've done, well, Jason Smith has done Purcell Factor of 5 with an NV center in a cavity. And so he's decreased the lifetime down to about, I just examined the student's thesis, 400 picoseconds, I think, for the NV center. From the natural 2 nanosecond or so you get an NV. And he's done that by using nanodiamonds. So he's put nanodiamonds into his cavity. He's trying to do the same now with the cadmium selenide quantum dot. But I think if you look at the volume calculations and you do a back of the envelope calculation, it's very difficult to get beyond a Purcell factor of 10. And that's not enough to get into the strong coupling regime. It's close, but not quite. So macroscopic cavities are hard.
You've shown these nice results about the molecular orbitals.
Yeah.
Do you plan anything, any further work on this? I mean, sort of, well, I mean, it's sort of a nice analogy, but then your particles are bosons and they don't interact. Or could you?
Oh no. So the idea. Okay. So the reason that you want to do the molecular analogy is this thing where you've got. Let's go back to this. The idea of the experiment in the beginning. If you have two molecules. 2 photonic crystals which are coupled photonically, but you've only got one dot in one cavity and no dot in the other cavity, right? Then in order to actually get emission from the antisymmetric mode, you have to actually excite one cavity with a photon, and because it's separated, you can actually then collect the light from the other cavity and not have contamination between the two. So you can do spectral and spatial separation. So you can then trigger the photon emission. So you're using the molecule as the quantum mechanics of the molecule to actually blockade your dot, to frustrate the emission, if you like, of your dot. So there you actually are using the molecular.
So there you're using
exactly, that's right. And that's the idea. But that idea was put out there about 4 or 5 years ago on a theoretical paper. It's a good, nice paper actually. It shows you exactly what you have to do, except you're just going to do it experimentally.
Any further questions? Oh, the one in the back, make me run.
Hello. I want to ask, is there any formula to calculate, I mean, how much shift of the air hole, and then how it can determine the envelope of the mode in
no, sadly, it's difficult. Well,
yeah,
okay,
because I really want to know how it can determine the envelope.
Yes.
Because,
okay, you can do it. So basically, I'm afraid you have to spend hours with a computer farm doing these calculations, because very subtle changes in the whole separation produce quite profound differences in the Q. One thing you do discover, actually, is that all the theories predict Qs that are about a factor of 10 higher than it can be realized experimentally. But they predict the splittings and the shapes very well. So if you want to know what the line width is, and you want to know where the energy emission is and so on, the FTTT calculations match perfectly with the experiment. The main difference is the width. And the reason is, in your FTTT calculation, all the holes are exactly identical, and they're all perfect. And of course, in real life, they're not identical, and they're not perfect. And so and what that does is it does, like in any system, say atomic system, you produce inhomogeneous broadening. So you inhomogeneously broaden the natural line width, if you like, of the photonic crystal by having these defects in there, and it's random, so you get a width broadening. So the one thing it doesn't. We did try this. We actually put in some randomness into the calculation. The trouble with doing that is it then goes up from 3 days to 30 days. but it does produce a broadening as we expected. So it does do what it should do, which is to make it worse. But no, I'm afraid there is no shortcut. It's really frustrating.
Okay. Thanks very much.